Hello all, and welcome to your next week of Chapter 5. We're going to keep talking about the Fundamental Theorem of Calculus, so get yourself ready for notes. If you have that page from last week talking about Part 1, recommend that we just keep going on with that. So get yourself ready for notes, and we're going to get started. Now, Part 1 we went through yesterday is this idea, last week, apologies, is this idea that the integrals and the derivatives cancel out. So if I have an integral and I take the derivative, I just get left with the function by itself. Now, the next place that follows is that this integral is equal to the antiderivative. Again, hopefully that follows since they cancel out. Equals the antiderivative. And if we have bounds, we just take the upper one minus the lower one. So this now gives us an ability to integrate a bunch more problems, ones that we wouldn't know exactly how to find the area for just by looking at them and using our geometry formula. Because x to the fifth, for example, doesn't have a lovely shape that's a circle, a triangle, a rectangle. And so we now have a new strategy, which is that we start with, if you have an integral, you want to find the antiderivative, and then we want to set up a difference, so that's a subtraction problem, of the bounds. And then all we need to do from there is evaluate. So let's look at a couple of examples for this. I'm going to make my pens a little bit bolder so that they're easier to read. So here we have the integral from 2 to 5 of x to the fifth plus 2x squared dx. So if you graph it out, you're going to look at a complex polynomial function. We're trying to find the area between 2 and 5, whereas before this would be very challenging. All we need to do is find the antiderivative. So what we want to do here is consider each term separately. So I'm just going to work separately. And then I'm going to recall our antiderivative power rule, which means that the integral of x to the n dx is equal to 1 over n plus 1 x to the n plus 1. So when I take each term separately, I've got x to the fifth becomes 1 over 5 plus 1, which is 6, x to the sixth. And then the 2 there is just the constant in front. And then I take x squared, which would be 1 over 3 x to the third. And what we'll keep doing is keep writing the bounds, which you'll draw a line like this, 2 to 5. And this is just notation to keep writing the bounds. You'll see all calculus teachers that you have either in college or high school or later on in any sort of course, any sort of environment, write your bounds with a line at the end like that. So now what we want to do is that's our antiderivative. So then we want to find the difference in the bounds. So what we do is we just take that antiderivative and we plug in our bounds. So 1/6, 5 is our upper bound, plus, and I'm going to simplify 2 times the third, 2/3, 5 to the third. So that here is our big F of b. So we're setting up a difference of the bounds with 5 as our upper bound. Difference minus, same function, but just with our lower bound of 2 plugged in. So 2/3, 2 to the third. And from there, all we're doing is evaluating. So then the area under the function x to the fifth plus 2x squared from the bounds of 2 to 5 is, if we plug this in, 2,687.5 minus 18. So the total area under that curve in that area is 2,671.5. Now the nice thing here is we can do it with things other than polynomials, of course. Here we've got sine of theta d theta. And just like with derivatives, it's just important that these ones match. They don't have to be always x. Same with derivatives, they just have to match. And we're going to follow the same process. We're going to ask ourselves, what is the antiderivative of sine of theta? Now, if you remember, d dx of cosine of theta is equal to negative sine theta. Since we have positive sine theta here, that means the negative has to be on the other side. So then the antiderivative here is negative cosine of theta, and then the bounds are pi over 2 to pi. Set up our difference, negative cosine of pi for the upper bound minus negative cosine of pi over 2 for the lower bound. And then we have cosine of pi is negative 1. So we have negative 1 for the upper bound minus cosine of pi over 2, which is 0. And the two negatives cancel out, so the area under that curve is 1. Looking at a final example, here, the way that I will always rewrite root problems like this, we've seen by now, this is the same as 0, the integral from 0 to 1 of t to the 3 over 2 dt. I'll use my power rule, which is 1 over 3 over 2 plus 1, t to the 3 over 2 plus 1, from the bounds 0 to 1. Simplifying that, we end up with 1 over 5 over 2, t to the 5 over 2 of 0 to 1. 1 over 5 over 2 is the same as 2/5. Plug in 1 for our upper bound, minus 2/5, 0 for our lower, and you end up with 2 over 5, since 0 to any power cancels out, and this is just 1. All right, so if you have questions about the connections here with antiderivatives and using the bounds to evaluate the area under the curve, evaluate the integrals, please let me know, and I'm happy to help you work through any questions you have.